Okay, so we're going to do a little session on something that's been in the news recently. It's the Event Horizon Telescope, and this has really sparked a tremendous amount of interest throughout the world. But it's also very closely connected to many things that we do in this course. So I thought I would try to bring that connection to some of the stuff that we've covered so far, and also incorporate it into Test 2. So there's been a little bit of a delay on the rollout for Test 2. Test 2 will be out, if it's not out already, depending on when you're listening to this, on Saturday, April 13th. And it will be due the following week. So black holes. Black holes are probably the most extreme object in the universe. What are they? Well, the simplest explanation is if we could take matter, we could take mass, and we could shrink it down to a volume of zero, we would have what's called a singularity. And a singularity is basically taking mass and compressing it to such a great extent that essentially it has no volume. If you remember, density is mass divided by volume. So we're basically pushing matter to the point where it has an infinite density. Now, when this happens, the gravitational field becomes so intense that even light can't escape. And thus the term black hole was used to talk about these objects, which were theoretical up until recent times. And the idea was gravity was so intense, according to Einstein's theory of general relativity, even light would not be able to escape. Now, nobody really thought of a way of taking a picture of a black hole because most of the black holes out there are actually quite small, no bigger than about the size of a city, and the closest ones are probably thousands of light years away. However, with this Event Horizon Telescope, we're actually able to take a picture, a radio telescope picture, of a very extreme black hole. These black holes are at the center of some galaxies. So again, black holes are, pushing nature to its greatest extent. We think of the black hole as having different parts to it. The singularity represents the place where the matter is thought to be, although because gravity is so extreme there, the matter itself may have just compressed itself out of existence. So, some theories have a singularity at the center, but really there's a region of censorship around the black hole, the spherical region called the event horizon, where nothing can cross it and never come back. That means that once light goes across it, it can't come back, and therefore, because light can't make it out of this event horizon, we can never see what's inside the black hole. What we would call a naked singularity would not be possible because of the extreme gravity. What happens beyond the event horizon is the realm of speculation. We don't have physics that can describe this yet. These are really quite fascinating objects. Now, because a black hole is nothing more than consume matter and gobble up light, even light can't escape it, it's not the black hole that we can actually see. What we saw was sort of the absence of light, the absence of light from the event horizon. The event horizon, I guess in a way, almost casts a shadow. That would be the best way to describe it, casts a shadow. And the reason why we were able to see this black hole is it's actively scooping up matter. And when black holes are near, stars, clouds of gas, or any source of material, that material gets sucked into the black hole, much like water going down a drain. Now, as the material gets close to the black hole, it actually forms a spitting disk of material known as an accretion disk. And this accretion disk gets really, really hot. It gets so hot, in fact, it glows mostly in the X-ray part of the spectrum and forms an ultra-hot plasma. This plasma is not just visible in the X-ray part of the spectrum, it's also visible in the radio spectrum, and that's how we were able to take the picture. Now again, most black holes that are near a source of matter will have this very hot accretion disk. The infalling matter will be incorporated into the black hole, but surprisingly, about 90% of the matter that falls onto a black hole is actually turned into pure energy. And with M87, we knew there was something at the center of it. Again, we're almost certain there was a black hole that was generating this huge jet of hot plasma. This was, we thought, the result of a black hole. Now, these polar jets escape nearly at the speed of light, and pictures of M87 actually showed these jets pretty clearly. Okay, now, some basic black hole stuff. We talked about several different types of stars, and at this point we're actually talking about the remnants of stars. We're going to begin talking about the remnants of stars. When stars die, they can basically become a number of different compact objects. Our sun will eventually die and become what's called a white dwarf. And white dwarfs are basically really, really dense matter. They're actually the core that's left over from the star. When our sun runs out of hydrogen at the center, it'll begin to fuse helium. And then when it runs out of helium at the very center, it'll puff out its outer layers, shedding its outer parts, but leaving the core relatively intact. And by this time, it'll be probably about 80% of its original mass, but no bigger than the size of the Earth. If you were to take a tablespoon of matter from a white dwarf, it would probably weigh about as much as a large ship. Now, that's what happens to normal-sized stars, like our sun. They eventually collapse. It's not a very violent event, but they eventually collapse and become this white dwarf about the size of the Earth. In even more massive stars, it almost seems counterintuitive, but they collapse violently. They implode inward, they fall inward, if you will, and then explode outward in an event we call a supernova. These don't become white dwarfs. The matter is so compressed, the gravity is so extreme, that in fact the electrons in the atoms are pushed into the nuclei, and it becomes a huge ball of neutrons, and that's why we call it a neutron star. A neutron star is no bigger than about the size of Manhattan, but it contains more than the mass of the sun, probably about 1.5 times the mass of the sun or more. The most extreme stars, they even leave a more bizarre object, and that's our black hole. I think it's beyond about 25 solar masses, although I should know the threshold. It does depend on the metallicity of the star. But in these cases, the core collapsed with so much force, or I should say the gravitational force is so great here that it basically crushes all the matter that's left in the core into a singularity. Again, that's when the mass is crushed to a point which has no volume. The density becomes infinite. Now the black hole, due to its gravity, sort of shrouds itself with this event horizon, and that's the black sphere that we're going to see in some of the images. If black holes are rotating, they might have sort of a distorted shape to them. The interesting thing is these rotating black holes, named after Kerr, who developed the equations to describe them, actually not only include an event horizon, but also have what's called an ergosphere around them. Black holes' gravity, being so intense, actually causes space to rotate around them. And there's a region called the ergosphere where even space and time has to rotate around the black hole. But again, the black hole, as it scoops up matter, basically funnels this matter into this thin disk of accretion material. The accretion material, or the accretion disk, converts gravitational energy into thermal energy, making the material right before it falls into the black hole really, really hot, okay? And this superheated plasma is what we're going to see on the radio images. What we can't see on the images are the jets of material which are escaping from the magnetic field lines of the black hole. Although they give off quite a bit of radiation, it's really the thermal radiation from the inner part of the accretion disk that's so bright it overwhelms everything else in the images. Okay, here is the core of M87. This was taken with a visible telescope. And the black hole is so small in this image, there's not enough resolution, that all we can see is the bright light coming from the accretion disk. But as it gobbles up matter in this accretion disk, it blows this matter into space. And we can see this matter in the form of these jets that surround the nucleus of this very large elliptical galaxy. And again, the accretion disk is just this very hot matter that falls into a black hole. This is actually the disk surrounding the accretion disk in a galaxy known as NGC 7052. And this is an active galaxy, meaning that it's actively giving off radio emissions from material falling into the black hole. So if we were to approach M87, as we got closer and closer to the center, we'd first of all see this cloud of material around it, this sort of torus or donut-shaped material around it. And then at the center of it would be a tiny, tiny accretion disk. So again, this is really magnifying the center of the galaxy using the Hubble Space Telescope with the greatest magnification that we can really reach. Now, no optical telescope is powerful enough yet to see the event horizon of a black hole. We just don't have that type of resolution. And if you remember, the bigger the diameter of the telescope's objective, the bigger the mirror in the case of optical telescopes, the better the resolution becomes. But again, even our best telescopes don't even get close to resolving the core of a galaxy. So we have to use a different technique if our optical telescopes aren't yet there. Radio waves, like visible light telescopes, are able to see material that's hot. Usually if something's hot, like the surface of our sun, it'll give off visible light. At much higher temperatures, matter becomes a plasma and will glow in the X-rays, but it'll also glow in the radio part of the spectrum. Here we see an active galaxy, but we also see massive puffs of material which are being ejected by the black hole and blown into space. Again, on this scale, the black hole is tiny. The black hole is probably only about the size of our solar system, and this is a whole galaxy. So the scale is not even close to what we'd see in terms of the black hole. Again, radio waves are great for seeing places where the gas is cool, but it's also very good for seeing plasmas. Originally, radio telescopes were, satellite dishes, so to speak. It would focus the radio waves onto a detector, and then that would be used to create very crude pictures. The problem is, because the radio waves are so much bigger than optical wavelengths, Like, optical wavelengths are like in half a micron region or half a micrometer region. So they're like about a millionth of a meter across. Okay? Radio telescopes are about 100th of a meter across, which means they have to be 10,000 times larger than optical telescopes just to reach the same resolution. However, we figured out a way to cheat with radio telescopes. What we see here is a single radio telescope. The image that we get from it would be rather poor and really wouldn't give us a lot of detail. If we want to see something very distant, like the event horizon of this galaxy, we need to have unbelievably large magnifications. We can achieve this by, instead of taking a single telescope, taking an array of telescopes, like this very large array of telescopes in New Mexico, and use them all together to create a higher resolution image. Now here's the problem. When we normally take a picture of something, we're only taking the picture using the energy of the photons. Now, most of the pictures that you see from the Hubble, from different observatories, they used to use photographic film in traditional observatories. Now everything uses CCDs. CCDs are pretty much work the same way as film does. The photons deposit their energy, the energy is turned into an electrical signal, and then we use a mapping of this energy to give us back a picture. Interferometers can't work that way. If we're going to use telescopes together, we have to have the amplitude, which is related to the energy, but we also have to have the phase of each of the photons or waves. So CCDs are great for taking traditional pictures with single telescopes, but if we're going to create an interferometer, this artificially large telescope type device, we're going to have to be able to match all the phases. And again, very, very powerful instrument, because the resolution that we can get is more related to how far apart the telescopes are and less related to how big the mirrors or the objectives are. So, how do we do this? Well, if we put our radio telescopes all throughout the world pointing at wherever we're looking at, a distant source, we point it to that and record the radio waves coming from that object, we can reconstruct the image and basically reach a fairly good resolution. Now here's, again, the very large array. Its largest configuration, where we can move the telescopes along, I don't know if you can see this track. You can move these telescopes along this old salt flat in the desert. We can get the baseline out to about 36 kilometers. Now, in terms of resolution, where 1 radian represents about 57 degrees, okay, we can get down to about 1/3 of a microradian, okay, really, really small. And that's about the best resolution that we can get from a high-powered optical telescope, okay? Now, this works because all of these telescopes are linked together, okay, and then their signals are recombined and reconstructed using computers. The problem is, if we want even better resolutions, we can't link the telescopes together like we can with the VLA. Now, the Event Horizon Telescope is not a single telescope, but actually a worldwide network of many telescopes located throughout the world. Okay? There's some telescopes located in Hawaii. There's some telescopes located in the United States. Some telescopes located in the deserts of Chile. There's even a telescope that was used down in the South Pole. Now, there's no way for all of them to communicate together in real time. So what they do is they use all of these different telescopes, again, all over the world, okay? The yellow actually are telescopes operating at 1 radio band, the blue are operating in another radio band. This gives us a huge baseline of 12.7 thousand kilometers. And when we do our calculations, we get down to 8 times 10 to the negative 10 radians. If we compare that to the VLA, which is comparable with typical telescopes, we are doing almost 1,000 times better, okay? About 500 times better, 500 times the resolution. But this is really, really difficult to do. Now, because the telescopes aren't linked like they are with the VLA, we actually have to take all the information in real time, convert the analog signals into digital signals. Before this is run, you actually sync a bunch of atomic clocks. The atomic clock will then code the signal to say when the particular signal, that bunch of data came in, and then they store them on hard drives. I'll tell you, I have a really big hard drive at home that I store all my computer stuff on a home network, and it can store like 4 terabytes, and it's not the size of a book. Actually, it's 2. I mirror the 2 drives together. Okay, so 4 terabytes is a fairly book-sized hard drive. They had to store 5 petabytes, which is 1,000 times more data than what I have on my hard drive. So they're basically at each of these observatories coordinating the run, so they're all running at the same time, coordinating the atomic clocks, dumping the data onto disks, and then they have to fly all the hard drives, because again, the internet's not fast enough to transmit 5 petabytes of data. They ship all the data back to the analysis point, and unfortunately, one of the telescopes was down in the South Pole. They had to wait for it to be shipped. I don't know if they flew it out or if they sent it overland, but that really delayed quite a bit of the time. And this is Kitty Bootman, who came up with the algorithm to basically crunch all this data down into a usable image. So there's some of the hard drives, each from the different observatories, and you can see, that's quite a bit of data, 5 petabytes. And she put the algorithm together, they ran this through a computer, and you can imagine crunching 5 petabytes of data, how long that would take. And that gave us this image right here of our first black hole. So what we're seeing right here is you can see the accretion disk around the black hole. Okay, that's what that I've highlighted that with black. Maybe I should use a different color. Maybe I'll use red. Again, this is the accretion disk. I don't draw very well with these circles. That's the hot infalling matter falling into the black hole. And if the picture were better, we might see something that looks more like this up here. Again, this really hot disk surrounding the black hole. And then at the very center, that is the event horizon. And because of gravitational lensing and other effects, the event horizons actually cast a shadow that's 2.5 times bigger than its size. So again, when we're looking at this, we're looking at the inner edge of the accretion disk surrounding the event horizon. And this is the first picture of a black hole. Now again, it's not a traditional picture. It's not a picture you might take with a cell phone, which would be visible light. This is a picture in the radio part of the spectrum. But again, it is a photograph nonetheless, even though it needed all those computers to process the information. Now, M87 was chosen because it was known that its central black hole was massive. Even though it's 53.5 million light years from Earth, its Schwarzschild radius, which is related to how big the event horizon is 1.2 times 10 to the 13 meters. And that corresponds to about 42 micro arc seconds. What does that mean? Okay, think about this. If you look up in the sky and you look at the moon is about half a degree. Okay? So the moon's half a degree. That's how much of the sky it takes up. If you break a degree into what we call arc minutes, the moon is about 30 arc minutes across. There are 60 arc minutes in a degree, so the moon's about 30 arc minutes. It's an arc second is 1/60th of an arc minute. So again, using the moon as an example, there are 1,800 arc seconds across the moon. So a micro arc second is a millionth. Oh gosh, this is not an easy thing to do. We're down to, again, 1,800 arc seconds for the moon. 42, forgive me while I do this math. Yeah, well, 42 is about 3. Oh gosh. So, roughly stated, about a trillionth about the size of the moon in the sky. That's how much we're magnifying it. Think about magnifying something to about 1 trillion times, and I'll double check that again. That's how big we had to magnify this. But M87 was chosen even though it's so far away because its event horizon is just so large. If we put our solar system in, it would easily be taken up by the event horizon here. And again, the event horizon depends on a few things. It depends on the mass of the black hole, and because the black hole at the center of M87 is much bigger than the mass of the Milky Way's black hole, it just has a much bigger radius. And it also depends on the gravitational constant and the speed of light. Now again, we're pretty sure that there's a black hole at the center of the Milky Way. We call it Sagittarius A star. And it's much smaller than the M87 black hole. But even though it's closer to us, it's also expected to be even smaller in the number of arc seconds, probably about only about 10 arc seconds across, about 4 times smaller than the image of M87. So the astronomers were smart. They're like, we've never done this before. Why don't we try to look at the biggest event horizon that we know, the biggest apparent size event horizon, and then we'll try to image the Milky Way's black hole, which we'll try later on. Now, we're pretty sure there's a black hole there because the stars that orbit near the black hole have ridiculously short orbital times. They fly around there, and only something with millions of solar masses could create the gravitational force that would be necessary to produce the orbits that we see. And again, we've never seen our own black hole, but we've seen at least the stars orbiting very close to it. So thanks to the orbit of some of these very close stars, we know that our own black hole is about 4 million times the mass of the sun, and this is much too massive to be the result of a collapsed star. And again, it's about 4 times smaller in angular resolution than the M87 black hole, but these astronomers are hopeful. So again, hope you enjoyed this recording. Just wanted to explain in the context of what we've learned in this course some of what's been in the news. Okay.